In the very first sliver of a second after the universe began, something had to be exactly right. Not almost right, not close enough, exactly right. Consider the glue that holds atoms together. If that force were just 1% stronger, hydrogen would fuse too quickly in the early universe, and stars would never get the fuel they need. If it were 2% weaker, protons could never stick together at all. The universe would be a drifting fog of lonely particles, no chemistry, no planets, no life. And this precision is everywhere. The universe's expansion rate, the strength of gravity, the mass of the tiniest particles, each one sits in a narrow window that allows stars to burn, planets to form, and creatures to exist. Shift any of them by a hair in the wrong direction, and everything goes dark and empty. But here's the unsettling thing. Nothing in physics demands these numbers be what they are. They simply exist, unchosen and unexplained, as if the universe were poised at a cosmic tipping point and has been for billions of years. Why? What's holding it there? And what happens to our answer if we discover that it isn't held at all? The question from our last chapter, what holds these numbers in place, was forced into the open by a man who wanted nothing to do with it. Fred Hoyle was a Cambridge astrophysicist and a lifelong atheist. In the 1950s, he coined the term Big Bang as a deliberate mockery, trying to make the idea of a cosmic beginning sound absurd. To him, the universe needed no creator, no explanation. It simply was. But his own work led him somewhere unexpected. Hoyle was studying how stars forge carbon, the element essential to all known life. Carbon forms inside stars when 3 helium nuclei collide and fuse. The problem? For that triple collision to work, the carbon nucleus must have a very specific energy level, positioned at exactly the right value. Without it, the helium nuclei would simply bounce apart. Every calculation suggested this level shouldn't exist. Hoyle predicted it had to exist because he existed, and when physicists measured the carbon nucleus, they found it exactly where his equations demanded. Exactly. Hoyle later put the shock of that discovery into words. He wrote, "A common-sense interpretation of the facts suggests that a superintellect has monkeyed with physics. These are not the words of a believer. They are the words of a skeptic who followed the evidence and found himself facing a door he'd assumed was locked." But carbon is only one slice of the pattern. The cosmological constant, the invisible energy pushing space apart, is set to about 1 part in 10 to the 120th power of its natural value. That number requires 120 zeros after the decimal point to write down. If it were slightly stronger, the universe would tear itself apart before stars could form. Slightly weaker, and gravity would crush everything back into a single, silent point. The room for error is not a window, it's a razor's edge, so the pattern repeats across every corner of physics. The constants don't just happen to work. They work with a precision that looks deliberate, as if the universe had been tuned, adjusted, set with care. And there is nothing in our laws of physics that explains why. That silence has a name, the fine-tuning problem. And it's the problem that would push scientists to invent one of the most controversial ideas in all of cosmology. But the controversy did not begin with Hoyle or with the constants. It began with a watch. Imagine walking across an empty heath and finding a pocket watch lying in the grass. The glass is scratched, the brass case dented, but when you pry it open, you see hundreds of tiny gears interlocked, each one turning the next, all moving together to tell the time. You would not assume that wind and rain assembled it. You would infer a watchmaker. In 1802, a philosopher named William Paley wrote exactly that scene into a book. His point was bigger than the watch. The natural world contains things far more intricate. An eye, a wing, a living cell, each is a machine whose parts work together for a purpose. Where there is purpose, Paley argued, there is a designer. Nature's order was evidence. At the time, the argument seemed unanswerable. A century later, a biochemist named Lawrence Henderson tried to put that intuition on firmer ground. In 1913, he catalogued what he called the life-permitting conditions of the universe. Water does something almost absurd. It expands when it freezes, so ice floats, so lakes do not freeze solid from the bottom up, so fish survive the winter. Carbon can form more compounds than every other element combined. Henderson argued that these properties are not random. The environment itself seems prepared for life, but Henderson's evidence was descriptive. It did not measure anything. That happened in 1961 when physicist Robert Dicke asked a different question, not why the universe is the way it is, but why we are seeing it at this particular moment. Dicke realized that carbon-based observers can only exist at a certain time in cosmic history. Too early, and stars have not cooked up carbon yet. Too late, and the stars that could make it have already burned out. The universe must be roughly between 10 and 20 billion years old for us to be here. And that is exactly what we observe. Dicke called this a selection effect. We should not be surprised that the numbers look life-friendly, because if they were not, nobody would be around to look. No designer required, no luck required, just the simple fact that observers observe. That idea was about to leave the quiet world of 1961 physics and explode into one of the most ferocious debates of modern cosmology. That idea, selection effect, sat quietly for 12 years. Then, in 1973, a young physicist named Brandon Carter walked into a crowded lecture hall in Krakow, Poland, carrying a paper that would name the unnameable. Carter was not trying to remove God from physics. He was trying to solve a puzzle. The constants of nature look impossibly fine-tuned for life. Dicke had shown that cosmic age matters, but what about the constants themselves? Carter asked a deceptively simple question. Imagine a cosmic casino dealing out universes at random, each with different laws, different strengths, different masses. How many of those universes would permit observers to exist? The answer, Carter realized, is almost none. So why are we in one of the survivors? The explanation felt like a cheat because it sounded like a tautology. We observe the universe to be fine-tuned because if it were not fine-tuned, we would not be here to observe it. No designer, no luck, just the cold logic of self-selection. A fish staring at water might conclude that water was designed for breathing, but a fish cannot imagine another element because a fish has never drowned. Carter gave this logic a name, the anthropic principle. The word comes from anthropos, Greek for human, but the principle was never truly about humans. It was about observers in general. Carter insisted on a weak form. Our location in the universe is necessarily special to us because we exist there. The universe had to look this way to us because we are inside it. Then John Wheeler stepped in. Wheeler was the physicist who coined the phrase black hole, and he had a habit of following ideas into dark corners. He proposed a participatory version. In his view, observers are not a lucky afterthought of physics. They are necessary for the universe to exist at all. The fine-tuning is real, Wheeler argued, because the act of observation brings reality into being. The constants are precise because observers collapse the universe into existence. But Wheeler's version opened a door that no one could close. If the universe requires observers to exist, and observers require a fine-tuned universe, then which came first, the tuning or the tuned? Most physicists stepped back from Wheeler's radical conclusion. They preferred the safer, weaker version, the one that doesn't require consciousness to build the universe. It only requires this. Observers exist, so the universe must be capable of producing observers. That is the whole argument. Think of a soldier walking through a battlefield after 1,000 shots have been fired. He finds one man alive. The survivor says, "They aimed at me and missed 1,000 times." But the soldier understands the trick. If the man had been killed, he would not be standing here making the claim. The survivor is not evidence of miracle. He is simply the only version of events that has a witness. That is the anthropic escape. The constants of physics look perfect for us, but we only get to see the universe where they were perfect. Every other universe with different constants has no one inside to notice. So the fine-tuning is not a sign of design. It is a selection effect built into the simple fact that observers observe. This argument has enormous appeal to scientists who want to keep physics free of the supernatural. It dissolves the watchmaker without ever leaving the realm of statistical reasoning. No God, no purpose, no intention. Just a cosmic lottery, and we are the ticket holders who happen to match the prize. To borrow from the physicists, We should not be amazed that the water fits the puddle because the puddle is shaped by the water. But here is the catch. A selection effect only works if there are many candidates to select from. One soldier surviving 1,000 shots is not surprising if 1,000 soldiers were shot at. But if there was only one soldier and he survived 1,000 aimed shots, you would look for another explanation. The anthropic escape requires the same. It needs a multiverse, a vast collection of universes, each rolling different dice with the constants of nature. Without many universes, the selection effect has nothing to select from. So the entire argument now rests on a single question: does the multiverse actually exist? And that question, it turns out, is far more dangerous than the one it was meant to answer. Does the multiverse actually exist? In the early 1980s, a physicist named Alan Guth found a mechanism that could create it. He was modeling the first seconds after the Big Bang and discovered that a patch of space smaller than a proton could balloon outward at an absurd rate, doubling in size again and again in tiny fractions of a second. Guth called it inflation, but the strange part wasn't that the universe inflated. The strange part is that inflation, once started, may never fully stop. Quantum fluctuations cause some regions to keep expanding forever, while others, like our own, pinch off into separate bubbles. Each bubble becomes its own universe with its own physics. This is eternal inflation. It produces an endless stack of universes, like foam on an ocean with no shore. But a universe needs more than empty space. It needs laws, constants, particles. Here, string theory enters the picture. It suggests that the fundamental building blocks of nature can settle into an enormous number of different configurations, perhaps 10 to the 500 different vacuum states. Each configuration would yield a universe with different forces, different masses, different chemistry. Multiply eternal inflation by the string landscape, and you have a cosmic casino that deals out universes with every possible hand. Suddenly, the anthropic escape becomes statistically inevitable. Most universes get the wrong constants. Some collapse instantly. Some are empty radiation. But among 10 to the 500 possibilities, a few will permit atoms, stars, chemistry, life. We are simply in one of those few. No designer, no miracle, no purpose. Martin Rees, the astronomer royal, calls this the most economical way to explain our cosmic luck. Paul Davies, who long resisted the idea, now admits the multiverse is a genuine scientific alternative to design because it turns a single impossible accident into a statistical certainty. And yet, this explanation is surprisingly fragile. It rests on two machines, eternal inflation and the string landscape, neither of which has been directly observed. And it raises a new question, more dangerous than the one it was meant to answer. What sets up the generator itself? If the inflation field and the landscape are themselves fine-tuned to produce universes, then the anthropic principle has not removed the designer. It has simply pushed the designer one step further away, into the machinery behind the machine. To generate universes, inflation needs a field, and that field must have a very particular shape. Imagine a ball rolling along a ridge. If the ridge slopes down too steeply, inflation stops in a fraction of a second. If it slopes too gently, inflation never ends at all. The ball must roll slowly enough to create many bubble universes, but fast enough to leave some energy behind for particles and light. That is an extremely precise requirement, and no physical law explains why the ridge has that exact shape. It is simply put in by hand. Then there is the vacuum itself. The string landscape says empty space can settle into many different configurations. But for any configuration to be real, the mathematics of string theory must produce a stable quantum vacuum. That has not been shown. Some physicists argue the landscape is not a theory of everything. It is a theory that allows almost anything. Without a proven mechanism, the multiverse is not a machine. It is a sketch of a machine that might exist. Even if the machine were real, the model has a deeper awkwardness. To say that life-permitting universes are typical, you need to count them. But the multiverse is infinite. An infinite set has no natural ordering. Compare two infinities in different ways, and you can get any answer you want. Some rules make life look extremely rare. Other rules make it look guaranteed. The multiverse only explains fine-tuning if you choose the counting rule that gives you the answer you already preferred. That choice is itself a hidden dial, so the generator has at least 3 dials: the shape of the inflation field, the consistency of the vacuum landscape, and the measure that counts universes. None of these dials is predicted by a deeper principle. They are tuned carefully to produce a cosmos that can contain us. The designer has not been removed from physics. The same fine-tuning that was supposedly explained has been relocated into the machinery of the multiverse itself, and that relocation changes nothing except the place where the mystery hides. The third dial is the strangest of all. It asks a question so simple it sounds innocent. Among an infinite crowd of universes, how do you decide which ones are normal, which ones are typical? Because if you cannot count the universes, you cannot say that life-permitting ones are common. You cannot say they are rare. You cannot say anything at all. Imagine a bag filled with an endless number of marbles. Some are red, some are blue. You reach in and pull out a red marble. What is the probability that the next marble is red? There is no answer. Because the bag is infinite, you could have 1 trillion red marbles for every blue one, or the reverse, or any mixture at all. Without a rule for counting, a measure, the whole idea of probability collapses. The multiverse is exactly that bag. It contains infinitely many universes with every possible constant, every possible law. So any outcome you observe has been realized infinitely many times. The universe you live in, with its precise ability to form stars and chemistry and minds, exists in endless copies. But so do dead universes, empty universes, universes that flash into existence and vanish before a single atom forms. There are infinite copies of all of them. Infinity divided by infinity is not a number. It is a blank space on a page. Physicists have proposed measures to fill that blank space, but no measure follows from the physics itself. Different measures yield different verdicts. One measure says our kind of universe is astronomically rare. Another says it is inevitable. There is no experiment that can pick between them because every measure makes the same observable prediction. You are here, observing what you observe, and here is the deeper trap. If the multiverse contains every outcome infinitely many times, then anything you measure, any particle, any galaxy, any cosmic pattern, is guaranteed to happen somewhere. The theory becomes unfalsifiable. Not because it is wrong, but because it is too generous. It predicts everything, and a theory that predicts everything explains nothing. What scientists are left with is a machine that cannot be tested. Other universes are causally disconnected from ours. No light, no signal, no imprint can cross the boundary between bubbles. They are forever beyond the reach of our instruments. So the multiverse does not solve the fine-tuning problem. It dissolves it into an ocean of speculation, where every answer is equally true and equally unprovable. And the question remains, untouched, underneath it all. Why is there anything structured enough to ask it at all? Underneath the multiverse, underneath all the dials and measures and infinite bubbles, sits a question that no amount of universes can dissolve. Why is there something rather than nothing? Physics is brilliant at telling us how things happen. It can trace a galaxy back to a cloud of gas, that cloud back to the Big Bang back to a quantum fluctuation. But every how ends at a wall. The wall is not a lack of data. It is a categorical gap. A mechanism can never explain why there is a mechanism at all. In 1714, a German philosopher named Gottfried Leibniz asked this exact question in a short book. He was not a scientist in the modern sense. He was a lawyer, a diplomat, a dreamer of grand systems. He had invented calculus around the same time as Newton, and the two spent years arguing over who came first. But Leibniz's deepest obsession was not equations. It was the sheer fact that anything exists. He reasoned like this: everything in the universe has a reason for being the way it is. You can keep asking why this planet, why this star, why these laws, and every answer points to something earlier. But if you keep going, you reach a cliff. There is no earlier thing. There is only the fact that something is there at all. That cliff is exactly where the multiverse stalls. A multiverse answers why our universe has the constants it does by saying there are many universes with many constants. But then the same question returns, one floor higher. Why is there a multiverse? Why is there a mechanism that generates universes? Why does the machinery exist, rather than no machinery? Philosophers call this contingency, the idea that everything that exists could, in principle, have been otherwise. Physics can describe what is. It cannot, from within itself, explain why there is and is at all. Some physicists wave this away as a question for theologians, but that is a confession. It means science, when pushed to the absolute foundation, goes silent. And silence is not an answer, it is the shape of the mystery. We can build infinite universes on paper, but we cannot build a reason for existence itself. The question stands patient, unlit, waiting for something that physics does not possess. On a windswept heath in the 18th century, a man bends down and picks up a pocket watch from the gravel. The case is brass, the glass is cracked, but inside, springs and gears mesh with such precision that he cannot imagine it assembling itself. He knows nothing of who made it. He does not need to. The arrangement of parts, the purposeful complexity, is enough for him to infer a maker. That man was William Paley, and his watch became one of the most famous arguments in history. Where there is design, there is a designer. For 200 years, science seemed to bury that argument. Evolution explained the design of life. Physics explained the design of the cosmos. The watch, it seemed, could tick without a watchmaker, but then something strange happened. The more precisely physicists measured the universe, the more the watch reappeared, not as a machine of gears, but as a set of constants, each one balanced on a razor's edge. A tiny shift in the strength of gravity, and stars could never form. A small change in the mass of a proton, and chemistry dissolves into a soup of unstable particles. The odds of these values coming together by chance are so astronomically small that calling them random feels like a decision, not a description. Enter William Lane Craig. He is not a scientist. He is a philosopher who has spent decades pushing science to its limits in public debates. His argument is not that the universe looks like a watch. It is that the multiverse itself looks like a machine that needs a maker. An infinite landscape of universes requires a generator, some physical process that breathes them into existence. But that generator is just another thing that exists, with its own laws, its own structure. It is a bigger watch, not a watchmaker. A mind, by contrast, is not a mechanism. It does not need to be generated. It simply is. This does not prove that God exists, but it does something quieter and more disruptive. It removes the intellectual embarrassment from the idea. After all, which is simpler, an infinite machine or a single uncaused mind? The question no longer belongs to physics. It belongs to philosophy. And that is where the watch has been waiting all along. The watch sits on the heath, and it is still ticking, but the hand that wound it remains invisible. We have two stories now. One says an infinite machine generates every possible universe, including this one. The other says an uncaused mind is simpler than any machine. Both are elegant, both are unprovable. Neither can be seen through a telescope or touched by a particle detector. And that is the honest truth. Physics has reached its limit. It can measure the constants to exquisite precision. It can trace the universe back to the first fraction of a second, but it cannot show us what lies beyond that threshold. The multiverse is a hypothesis, not a discovery. The designer is an inference, not a measurement. No experiment has ever confirmed another universe. No observation has ever produced a divine signature. Each side stands on logic alone. Some physicists try to dissolve the tension with the anthropic principle. The constants appear fine-tuned, they say, simply because we are here to see them. If they were different, no observers would exist to wonder about them. It sounds like an answer, but it only moves the problem one step further back. It explains why we live in a universe that allows observers. It does not explain why there is a universe at all, or why the generator behind it exists rather than nothing. It is a subtle observation about our own existence, not a solution to the mystery. But here is something remarkable. This unanswered question is not a failure. It is an engine. The mystery of fine-tuning has driven physicists to measure nature with absurd precision. It pushed cosmologists to imagine structures beyond all imagining. It forced philosophers to sharpen their arguments until they gleam. A question that produces that much labor is doing real work in the world. It does not need a final answer to be valuable. And maybe the most honest position is simply to live inside the uncertainty. The universe is under no obligation to explain itself to us. We may never know why there is something rather than nothing, or whether the constants were chosen, or whether they are just one roll of an infinite die. Standing at that cliff, feeling the wind, is not a failure of thought. It is the beginning of wonder. We would like to know where you stand. Do you see a watchmaker behind the fine-tuning, or an infinite generator, or are you comfortable with the question staying open? Tell us in the comments. We read every single one. Thank you for watching. Keep asking. So the watch remains on the heath, and the heath remains. We have walked the full circle, from fine-tuning to anthropic principle to multiverse, and back to the silence of the unknown. Each explanation moves the mystery one step further, but never dissolves it. The question stands, not because we are too small to answer it, but because the question is bigger than any answer we have yet constructed. That is not a defeat. It is the shape of a genuine mystery. Where you stand in that mystery is your own, but standing there and asking is what keeps the search alive. We would love to hear which side of the cliff you find yourself on. Write it in the comments. We read each one. Thank you for watching and for thinking with us. The question remains, so do we.